for skill in the information paradox. I gave John a baseball encyclopedia. Maybe I should have just given them the ashes. Between 1970 and 1980, I worked mainly on black holes and the Euclidean approach to quantum gravity. But the suggestions that the early universe had gone through a period of inflationary expansion renewed my interest in cosmology. Euclidean methods were the obvious way to describe fluctuations and phase transitions in an inflationary universe. He held an uphill workshop in Cambridge in 1982, attended by all of the major players in the field. At this meeting, we established most of our present picture of inflation, including the all-important density fluctuations, which give rise to galaxy formation, and so to our existence. This was 10 years before fluctuations in the microwave were observed, so again in gravity, theory was an end of experiment. The scenario for inflation in 1982 was that the universe began with a Big Bang singularity. As the universe expanded, it was supposed somehow to get into an inflationary state. I thought this was unsatisfactory because all equations would break down at a singularity. But unless one knew what came out of the initial singularity, one could not calculate how the universe would develop. Cosmology would not have any predictive power. After the workshop in Cambridge, I spent the summer at the Institute of Theoretical Physics, Santa Barbara, which had just been set up. We stayed in student houses, and I drove into the Institute in a red electric wheelchair. I remember my younger son, Tim, age 3, watching the sunset on the mountains and saying, "It's a big country." While in Santa Barbara, I talked to Jim Cardle about how to apply the Euclidean approach to cosmology. According to DeWitt and others, the universe should be described by a wave function and a Bethe-Wheeler-DeWitt equation. But when picked out the particular solution of the equation that represents our universe, according to the Euclidean approach, the wave function of the universe is given by a Feynman sum over a certain class of histories in imaginary time. Because imaginary time behaves like another direction in space, history theories in imaginary time can be both surfaces, like the surface of the Earth, with no beginning or end. Jim and I decided that this was the most natural choice of class, indeed the only natural choice. We had sidestepped the scientific and philosophical difficulty of time beginning by turning it into a direction in space. Most people in theoretical physics have been trained in particle physics rather than general relativity. They have therefore been more interested in calculations of what they observe in particle accelerators than in questions about the beginning and end of time. The feeling was that if they could find a theory that in principle allowed them to calculate particles scattering to arbitrary accuracy, everything else would somehow follow. In 1985, it was claimed that string theory was a Selfman theory. But in the years that followed, it